Okay, let me started. Hope you're all good. You wanna be here with our lecture?
I think like having calculus on Sunday.
Yes, Infy 2, lecture 2. Coincidence? I think not. Let's see. On Tuesday, what's Wednesday? Next lecture is Tuesday. Wednesday it's Infy 1. We come to lecture number 3. Okay, so a little reminder. Last week we talked about derivatives. The main problem is technical, or at least stated like that. We have a function, some function f, and we want to find standard derivative. Which function we're gonna derivate to get our real f. And we mentioned that the question generally it's not so simple. And our plan will be done it in lecture number 1 and in the practice as well, this week as well. Next week we will start something else. Is to have a look at some of the methods of finding such antiderivative. And we've already seen the integration by parts method. So let's have a reminder. Don't know if that's actually how you say it. You all understand me? Integration by parts. Integral of f of g tag is fg minus integral of fg. We'll show some examples where we would try this method of integration by parts. We'll try to find an antiderivative, like a multiplication of two functions, especially when it's a polynomial, a single function or a long function, I called it last week. You put it like 1 and this function and go on. And today, I want to talk about another method, change of the variable, changing the variable in the integral, called substitution, something like that. I don't want it to take all the lecture long, so after I think we went through everything I want, I'll continue with another method. And this method is a bit long, take it to the next lecture as well. But first of all, we start with our changing the variable. In Hebrew, I call it החלפת משתנה.
That's substitution.
Substitution, yeah. But it's more than that. And when I say substitute, I just imagine with the, instead of x to the square, I put t, and that's all. It's a bit, I want to say harder, but more than substitution, but you can call it substitution, it's totally fine. The question is simple. Bucket or no? Do I score it, yes or no?
What?
Do I score it, yes or no, to the bucket?
No.
No.
Yeah. Zero
I'm
faith.
making more challenge.
Zero faith. Yes.
Almost. With the buzzer be like. Yeah. So the real question is,
Yeah.
what are we going to do with the dx? I mean, and as I said, yeah, last week.
Dx is important, but we didn't say what it is. It's a derivative of x, which is 1. No, like last week we said dx is important, but we didn't say why.
The dx.
Yeah.
Yeah. So this week, I don't know if we're going to talk about its importance or what it actually means, but we have to pay the toll. I mean, if we have the integral of fx dx, and for some reason we want to change x with t, then the dx should also be substituted with dt. And the question is how? And before the y question, yeah.
Then we need to firstly to do definition of the t, like what we
Yes.
Yeah.
And the questions are always combined. The question, how do I do it, and why do I want to do it? And integration of parts, we first started with how we do it, and we started from a derivative rule of the multiplication, and then we got the answer why and where we're planning to do it. So here we're trying to do the same. First of all, how do we change the variables, and then why would we like to do so?
Yes.
And have a couple, 3 examples. So the integration of parts comes from the rule of how do we derivate the multiplication of functions. How do we get the changing of variables from where? When we talk about derivatives, so we know the chain rule. If we want to derivate f with g inside her, we do it that way, and this way, f gx, and we multiply it with g tab. So if we put the integral on both sides, we get f g tab and integral of f tag g tag x. And you already know that integral and the derivative, generally speaking, as we do now, cancel each other. We get fg without integral, which means we've already calculated the integral. So when it comes to the change of variables, we have integral of fgx g tag x dx, putting, denoting, whatever, different letter t, the t. In Hebrew, I always say t חבר אמיתי. How to I trying to translate it to English with bread? I don't know. Another letter. Putting t equal gx, we get that dt is g tag x dx, and then the integral of f tag gx g tag x becomes the integral of f tag t dt, which is ft. Of course, we can go back, actually need to go back to the original variable, which is x, and when we end, let's see, when we end our calculations, we always add this plus c. And I call that changing the variable or substitution you want. And rectangle people, we have this. If you put t is gx, then dt, which we need to have in order to calculate the integral, is g tag dx.
Maybe u is there for you.
U is there for you. It's roll it all on my tongue a little bit. U is there for you. Another way to think of how we get this equation is actually just the notation, but you can explain it. If we look at it this way, P is GS. And we have a notation for the derivative, putting dx like this. We derivated both sides. Here we denoted it with the tag, and here with the dx. And now, magically, we multiply both sides with dx, magically because it's just a notation, doesn't it? Isn't it? Or whatever. But we get dt g tag x dx. So the bottom line is that about the how. If you want to put in t instead of gx, substitute t instead of gx, then if you have to put dt, and it has to be g tab dx. And now we can get straight to the why, or when, or where. We will try, please try, yeah. Don't promise anything about succeeding, but we'll try. So, but the eraser.
By the way, for anyone who is never works, this is really good for the first few parts of question 3. The first one, first percent of different indexes. Oh, no one over that until
Okay.
It's just using some trigger, today's thing.
Yeah.
So, when, where, how, why would I want to try and substitute instead of gx? Let's say now, when we see a function, in Hebrew I say مسحكت, I mean plays with having a little game, a little fun with her derivative. Let's put it like this, having fun with its derivative. We can try P equals gx. That's a wonderful sentence. Take photos, send to your parents, look how fun. But it's, as I like to call it, general description. We must be examples in order to start to understand. So let's have an example. For instance, something simple. A number you all love.
42.
42. Yeah, fancy for everything. Let's put it 42 octangle x above x squared plus 1 dx. What do we add? We already know to not be afraid of numbers, especially constants. We can just put them away when it comes to integrals. And talking a bit practicing language, how do I actually get to the exercise? I can see the function rectangles, one hand, and its derivative, 1 above x squared plus 1 on the other hand. So, in order to see it more clearly, I can write it this way, 42 outside, Hishta, and arctangents x 1 above x squared plus 1 dx.
Oh. Wait. No. Yes. I mean,
First of all, yeah.
Yes. I mean, first of all, yes. Now, but what's the derivative of arc then?
This dude.
Yeah. Okay.
This little guy, 1 above x squared plus 1. And then, was first example, so it might be simple. It's good. It's a good start. If we put
T equals x.
T or U, whatever you like, arctangent 6, we get, I'm going to write it here. Wait, this will dt is the derivative of arctangent 6 dx, which is on both x squared plus 1. And how convenient we get our integral 42. How good you think to be? Arctangent 6 dx becomes this is t. These sacrifice it and we summon dt. We get 42 the integral of t dt, which is an immediate integral I called last week. It's t squared above 2, and it's mandatory go back to the original variable. It's 21 arctangents x power of 2, and we finish always adding plus c. As I mentioned last week, I think I mentioned, we can always check ourselves. You can now derive this function, and hopefully you get the function inside the integral, which we call the integral. So when I see function, having fun, playing, having a little game with the derivative, we can try. So we're saying, not promising anything. Integrals of finding any derivatives are much difficult, harder than to find the derivative. But we can try and put t is the function, and we pay the price with the dt is the derivative dx. So that's our first example. Pretty simple. I want to solve another one, a bit harder, from exam. Was last year or the year before that, one of the exams. We have in the last 3 or 4 years, we have Infi 2 in semester A and semester B, and each semester has at least 2 exams. With all the war and the Miluim, we've got a lot of term C, term D, term E, term F. Infi 2, semester B, 2 years ago, Tafshin Peidaled, I had 6 different terms. A lot of people were in Miluim and stuff like that. So the last one was almost a year after the semester actually ended. Yeah. Well, it got good. Not promising anything, but when it comes to me and terms after term B, C, D, etc., I usually just take half of term A, half of term B, and mash them up into one new, freshly new term. Okay, another example, which is gonna be a bit harder, but not so hard. Another one. was something like that. I'm not sure. Don't wanna ruin the party, but it was like ln cosines x sinus of 3x, something like that. Yeah. Step 4. So first, we recognize the two functions, cosinus and sinus. One is the derivative of the other. So don't be afraid of the minus. We can also, you can always put it outside or inside. It's a constant. So the question is, what do we actually substitute? Do we just substitute t is cosinus x and then we pay the price with the sinus, or vice versa? And the question is not so hard because the derivative should be here alongside with dx. So we probably want to substitute t is cosinus x, and then we have dt sinus x dx. The minus, we'll deal with it later. It's all fun and games, but we have sinus to the power of 3, not just sinus. So here, what was expected from the students in this exam was, first of all, make sure we have sinus here, and not sinus to the power of 3. We also know, I called it last week, trick shofel in Hebrew. Couldn't find the exact English word for shofel. I think it was called nefarious or something like that. That's it. It's not 100% fit. Instead of sinus to 3, you can write sinus to another sinus. And here, well, we have in mind t is cosinus x, and then dt will be sinus x dx. Another question emerges. What are we going to do with the sinus paribua, with the sinus squared? We have to write it down in the terms of cosinus. So
it's 1, no.
Yes, it is.
It's 1 minus cosinus.
And the important question here is not why is it true. You know, it's a basic identity. It is why we do it specifically that way. This loop looks more complicated than this one. It's all complicated. But instead of sinus, we have cosinus and sinus. But now, if we put this cosinus x, we get dt is the derivative of cosinus x dx, which is minus sinus. Perfect, whenever I'm wrong, of course. And well, we can put the minus here if we actually want to get exactly what we have in our integral. And here, with this substitution, we get this ln t. This one is 1 minus t squared. And this one is minus dt. Without writing sinus squared as 1 minus cosinus squared, we couldn't write the integral, all the function inside of the integral, in the terms of t, which is necessary in order to calculate the integral when you substitute the t instead of x. So now we have ln t and 1 minus squared and minus dt. And after a little organization, we get ln t, let's put it right next to the dt. We got t squared minus 1 ln t dt. Substitution did make the integral simpler, but not immediate. And when it comes to a question final exam level question, we should expect it. I mean, try something, if we move forward, it gets us somewhere, but not to the end of the question. Now we have a multiplication of functions. One of them is a polynomial. So what are we going to do here?
Distribution.
We called it integration by parts. Exactly. So using two methods, a bit of trigonometrical or trigonometrical, whatever, identity, some razzle dazzle, and you get to the solution. So let's finish. I mean, the example of how we use the changing variable is done, but the question is not done, the exercise is not done. So let's finish it. Here we can try integration by parts. So let f be the line t, and that is going to be the one above t. On the other hand, g tag is t squared minus 1, which means that g itself is t to the power of 3 above 3 minus t.
Yeah. Just to know why don't we just distribute LT in this case and just do the difference, like the difference of the integrals, like the integrate t squared times.
Oh, we can do it. We can do it. I don't think it's gonna be easier. We will have the integral of t squared ln t, which requires the integration by parts.
Yeah.
Let's do integration by parts
Once.
Yes. But what do we get here? Let's write it down slowly but surely. If we have a variable at t squared minus 1 ln t dt, using a different color. Technically, we have here that's fg tag. So it's gonna be fg, which is to the power of 3 above 3 minus 2 ln t. This is fg minus integral of fg, which is 1 above t, and our little precious g. Now, yes, things are going nice here. Get t squared above 3 minus 1 dt. So both of the components here are immediate. One gets this is third defined with to the power of 3 above 3. 1 becomes t. And our final solution, final bottom line, we have to get back to the original variable, which is cosine sets when it comes to t. So we have cosinus third x above 3 minus cosinus ln cosinus minus cosinus third above 9 minus is plus cosinus x, and the end of all plus C. Look at my nice little wound. Go safe into a fight. A fight with my daughter's kindergarten door. And some chunk of metal, just and it opened it. Nothing. It's me outside. So I reached for the handle. I looked at the handle. Not here. So it just pierced my head. Yeah, go to the ER. Got my wife a little nervous. It's fine. Good. So if I didn't make any mistake, then promise anything, of course. This is our final solution. If you derive this function, you should get this one. So first of all, it's much complicated here to calculate the derivative and be sure that we didn't make any mistake. And moreover, when it comes to trigonometric functions, one can find the function. It's the true solution. It's fine. It just doesn't look like the solution, the formal solution, or something like that, because you used this trigonometric identity, and the lecturer used another one, and they both were right, of course. But when you try and compare it, it looks different. So, as I said last week, we don't recommend derivating the function we got in order to get the function here to see if we are right or wrong. Solve the question, got some bottom line, you add a plus C, move on to the next question. Best man can get.
Try to derivate this question and spend half an hour.
Don't check yourself or you shrink yourself. If you know, you have 3 hours, 2 hours, you finished everything, got an hour for self checking, go for it. Goes, but
Meditation
just doesn't happen. Question about our example?
I think smart to ask now.
Yeah.
Okay. So I want to before our last example, I want to speak of the chaining variable more generally. What do I mean? What we first show in our journal description and then both examples, we substitute an expression, a function of x with t, or whatever level you like. But one can think of some more general idea, substitution, and where we substitute an expression of x with a different expression of t, or u, or whatever, not just t itself. I'll start here with the example. Then I'll explain how we do it, and we'll actually do it. The example. Let's say we have this interval. 1 minus. We can take a different number, but let's do 1. Then you say square dx.
Yes.
Yes. It's not an immediate one.
We have this in our phone. Did we have this in our phone?
Yeah, we have
Thanks.
Yeah, so don't tell anyone. So the idea, trying to build it with you, is something like that. The square root is annoying. Without the square root, we could solve it easily. Nobody likes square roots. Yeah? Without profanity. Let's go on. the square root, it's not going anywhere. Yeah.
You're looking to t equals like everything in the square root, like to get the.
So, interesting idea. I'm not saying it's not going to work, but you can try and see. When you have a square root, one way to try to go forward, I'm not saying it's going to succeed, is to put everything in the square root as t. Then we see what is the price we're paying with the dt. Hopefully, it will somehow get along. It might work. Maybe I'll be honest, it might work. But I have something different in mind. Something like, how can I cancel the square root, make it go away? When we have something squared in the square root. I mean, let's say that. So u squared, square root is just u. Or absolute value of u. If you are a pedant. Now, when we have 1 minus x squared, I can think of it that way. The 1 is annoying. It's not the square root, it's the square root and the 1. The combination is annoying. If one can put, let's say, sinus instead of x, we can get the square root of cosinus squared, which is just cosinus, and we can go on. So the question here is different than what we've already done today. We don't want to put t instead of some expression of s. On the contrary, we have x, and we want to put some expression of t. And as I mentioned, we can ask ourselves the question itself in the most general way possible. How can we substitute some expression, let's call it h of x, with a different, or t with a different expression of x? Let's say instead of x, we had here like, I don't know, number you like? Huh? And another place, let's say 4.
Which 21 is that?
Okay. So if we know how to substitute 2x with sinus t, we'll get this one, which is solvable. So the general question is that, how can we substitute an expression of x with an expression of t? And not just with the t itself. So, technically, it's very similar to what we've already done. If we want, generally, putting an expression of t instead of expression of x, we get h tag t dt is g tag x dx. When ht is just t, what we did in the last 2 examples, we get t tag, which is 1. Just dt equals g tag x dx. So, with this way of knowing how to substitute between 2 variables as generally as possible, we can solve this question. For example, so if we put sinus t is 2x, then sinus t tag dt is 2x tag dx, which means that cosinus t dt is 2dx. Yeah.
We're gonna learn about Weierstrass substitution.
Okay.
Are we gonna learn about Weierstrass substitution?
Weierstrass?
It's kind of like T-ball.
No. No. I mean, they are very. One can go down very deep into the world of specifically substitutions and generally methods of finding the antiderivative. As I mentioned, we do 3 lectures for this subject, nothing more. And we have a much very wide field of Euler substitutions, and you mentioned Weierstrass and etc. etc. A lot of names of dead people. And I will keep it simple. Keep it simple. First of all, when you recognize this game between play between function and its derivative, you try and substitute t is the function. And secondly, more generally, when in more, let's say, freehand, yeah, we think a little, yeah, probably putting sinus t here is gonna help it. So how do I do it? And then we'll explain how to do it generally, putting ht and gx, etc. So, as I started to say, we actually want to change dx to a term of dt. So I'll write it that way. Dx is cosinus t above 2 dt. And what do we get? The integral of 1 minus 2x squared into x becomes integral of 1 sinus squared t. And dx becomes cosinus t above 2 dt. As well, they written in blue. This is just cosinus t. And cosinus t above 2 t. And we get here cosinus squared dt. That is fine, very nice. Without square root anymore. On the other hand, the integral we got is not an immediate. Just like, last example. After we applied our method of changing the variable, we didn't actually quietly finish the question, but we did move forward. So now what? So when it comes to trigonometric functions, the trick, basic concept, is using the identities in order to lower the powers of the complexity, of course, of the powers of the functions. I mean, if instead of cosinus to the power of 2, we have just cosinus, it's an immediate integral. So how do we lower the power of a trigonometric function? First of all, I must say we actually saw something like that in our last example. We had like sinus to the power of 3, and we put aside sinus to the squared, we made it the cosinus, and then substitute, and the power is gone. We had ln t and t or something like that.
Is it? I don't know if I remember correctly, but is it like 1 plus cosinus of t over 2 or something?
Yes. When we got the square, cosinus square or sinus square, we use the identity of we call it double angle, because the big כפולה. I have it in like this. In cosinus 2t is 2 cosinus squared t minus 1. Yeah, of course.
Why not?
So, and now we can, have cosinus בריבוע t to actually be 1 plus cosinus 2t above 2. Putting the 2 outside, it's already 4 down there. We get an immediate integral. 1 becomes d. Cosinus is sinus. Don't forget the 2 in the denominator because it's if we call it the inner derivative. Checking my time. This is t. This is sinus 2t above 2. Remember, get to the original variable, which was now we have a little problem. We need to go back to the original variable, but we do not have t or sinus 2t as an expression of x. Yeah. So first of all, what can men do? They can try and have some identity sorcery in order to put it in the terms of sinus t, which might work. I won't be very good, but simple solution to our problem is to actually understanding what is t, not just sinus t, but t itself. When you have sinus t is 2x or whatever it is, and you want to get rid of the sinus, what do you actually do? You put a little arcsinus friend, of course. So t is arcsinus of 2x, and we get here one ugly little fella with all this arcsinus. We don't get our grades, we don't test our knowledge based on how beautiful the functions are. It's totally fine to have sinus, arcsinus, whatever. Above 2, and do not forget the plus c at the end. Yeah. I missed one, yes. How do you call it? Parentheses?
Parentheses.
Parentheses.
Brackets.
Brackets.
Yikes.
British English, man.
Yeah, barely English at all. So
A British English is barely English at all?
It's a long story. Anyway,
Why is it?
How?
You're not right.
It's the original one.
No, actually, the American is more original now, but that's another story. Because there were changes to English after it went to American. It's a long story.
Whenever an American says me, you've got an Israeli accent, I think, man, you've got accent as well.
I'm not American, but yeah,
it's not called Americanish.
Yeah. So arcs. What I didn't know this when I started the homework, and when I did the part of the homework that necessitated this, I looked it up online. What I don't understand. Yeah. What I don't understand is how can we we need the inverse function of sine to get back to x, because instead of changing x with t, we just express t in terms of x in terms of t, right?
Yeah.
So what I don't understand is arc sine is a limited function. It can't represent every value, right? Because
yeah, it's not a problem. I mean, if you go back to the original question, not every x is in our domain. You can put x 2, for example. You got something negative under the square root.
So, but if there are there limitations to this technique that we can't use it here, but we can use it there, kind of thing?
When it comes to finding the antiderivative in our integrals, the answer is no.
Okay, so we just use it and ignore the limitations of sine and arc sine.
Yes.
Sure.
And mathematically, they are here. When I first write the question down, it's not working for every x. So putting t is arcsinus of 2x, for example, this specific question is actually kosher, mathematically speaking.
Yeah, but what I mean is that
we don't get deep into that.
If it works, shouldn't work. Sure,
why is it true? What?
We don't really get deep into why it works or it doesn't work. Okay. No.
More questions? Okay.
Now we go into partial fraction.
Yes.
Got it. Yes.
How did you?
Because I did the homework.
Okay. Didn't you say it's for 2 weeks or something? Or?
It's until the 10th of November. So
what? Remember the 10th of November.
No, yeah, but we might get another homework this week.
Yeah, you're probably right. Oh, you've got like a half. Oh, I think it's gonna teach up.
Yeah.
Yeah. So for our next and last method, which will last to the next lecture as well. I first want to show you the problem, the kind of functions we want to find their antiderivatives, and then we'll start to explain how we do it. It's a long, exhausting, very boring process sometimes, but it's part of the syllabus, so we're gonna do it. And when you solve, I don't know, 3 questions of such, you'll master it as well. It's not complicated, just long and boring. So what kind of functions we talk about? We call it rational functions. Getting harder and harder finding rational people, so we stick with the functions. A rational function is what do you say in the math?
Fraction.
Fraction is shevel.
I mean,
You understand. The fraction or f fraction, that's right. Formally, a fraction px above qx is called a rational function. Where or when p and q are both polynomials.
no, they're not reducible.
Hmm?
And they're not reducible. How do they say?
Not necessarily.
Yeah.
Just polynomials hang with each other. I call it rational function. For example, x to the power of 6, and let's say x to the power of 3 minus 1. So, I mean, I already wrote the integral on the dx here, but the rational function is actually the function itself. And we want to find an anti or the antiderivative of such function. The process contains 3 steps. Each one can be very long, depending on the function. But putting homework aside, when it comes to the final exam, you have 3 hours. We have something like 26 lectures along the course. I can't have 2 hours of the exams, 3 hours, being you're spending on calculating one simple integral. So even though each one of the steps can be very long, exhausting, when it comes to the exam, if such an example will occur, probably 1 or 2 of the steps will be very easy and only one will require some work, not very hard work. Yet again, homework is different question. As I said last lecture, last week, here is a big boy, he decides whatever he puts in the homework, etc., etc. And you do have time to do your homework, and you can use GPT or whatever you like. So if a question or 2 Your homework is a very long one. Don't be afraid. Be not afraid. Exam won't be that ugly. So, what are the 3 steps? The process. We have 3 steps in order to calculate the integral. First, we have to lower the power of the polynomial in the numerator so low that it becomes lower than the power of the denominator. Okay, the power, the degree, it's a more accurate term. The degree of the numerator. Any typo, correct me, please. Should be lower, smaller, whatever, and then the degree of the denominator. If the function you're given is already in this configuration, you got greater power in the denominator, you can move forward to the next step without doing anything. How do we do? Well, I write now very generally 1, 2, and 3, and then we'll talk about 1. This is enough for this lecture. Next lecture, we'll talk about 2 and 3 and move on. So how do we do it? We do it, yeah.
Maybe change the variable.
One can think of change the variables in specific cases, but I want a general answer which is working for every case. It's called in Hebrew chalukat polynomial. I mean, dividing the polynomials. Exactly what
Polynomial division.
polynomial division. We use polynomial division. And I stop here. Write 2 and 3, and then we'll talk about what is actually polynomial division. You may have seen it in a different course. I don't think you did. Maybe a little in Infi 1, when you want to calculate the sum of some series, and it's you. No, I don't think.
I mean, I can check my homework. I remember using long polynomial division for something, but I don't remember exactly what.
Yes, we do the long one. I'm not assuming that you know it, so we'll explain it. For roughly. 2. After you have the lower power in the numerator, one can write the fraction as sum of what is called partial fractions. Sum, the sum no, of partial. For example, a very simple one, when you have 1 above x squared means 1. One could write it as 1 above x plus 1 minus 1 above x plus 1. And in order to get actually 1 and not 2, you can add the half or something like that. Multiply by half. So what you actually want to do in the general case, what is a fraction and a partial fraction, we'll get to it. Now, just writing it in. Generally speaking, and three. After all the fun and games, the la'ba in Arabic, you actually have to calculate the integral. We calculating. Turn it to gerunds. Calculating.
The integral.
Huh?
The integral.
Yeah, the integrals of the partial fractions, which we got step 2. When it comes to one above x minus 1, the integral is immediate. It's just ln of x minus 1. But to say that there are more complicated partial functions, so complicated methods of calculating their integrals. As I said, the process can be long, exhausting, and it not just can, it probably will be boring. That's something we need to do. And this is just the headlines of each of the steps. Now let's talk about step 1. What is actually polynomial division, or as I said, the long polynomial division? Maybe you've already seen it somewhere, and I'm just reminding you. Maybe it's new to you. It is similar to a long division of numbers. Everybody has seen it, but in elementary school. Not kidding. Here in Israel, it is taught in the 3rd grade. You get some nice 2 digits or 3 digits number. You want to divide it with a little number, smaller number, and you do the right angle stuff of, let's say you want to divide 360 with 15. So write it like the way. Remember such things?
Yeah.
So now I'm going to explain from the start. Beginning, when it comes to polynomials, but the concept is the same. The concept is the same. So let's have our headline, polynomial division. If you want to add the word long, you might do so. Yeah, no, it's not. It didn't happen to me here. Happened to me last week or 2 weeks ago. I had some preschool course for the engineering students before they actually start to learn math. And the clock in the computer was totally different from the real clock. And I went with him with it, and they all sat down like 2 hours. So poor and neglected without a break. So when I look at my phone, it's different time from the computer. I should remember it. I'm going to write it in a very basic language, not just because I'm not a native speaker, but because I want it to be written that way. So when we come to an example, we can apply it easily. It will be a bit long or a bit not well formulated, but I think it's good. Let's all the numerating, let's start with A. First of all, how we divide the polynomials? We put the bigger one with the greater power under this, I don't know, right angle, and the other one on the side. It's a nice, easy way to write it down that way. But it's just the right. What we actually do? We divide. Let's write it like divide the greatest power of the denominator with the greatest power of the numerator. Okay, I write down everything and then we'll apply it. Example, probably 2. Secondly, what we got, we take what we got in level A and multiply it with the numerator and C, we take what we got in B and we write the difference between this and the denominator. Difference between the denominator and that. You do it until step A gives us fraction. That's a nice soup of words. Write it down if you want. And then we'll have an example. Probably, let's see how we roll. Another one. Now playing, we're going into step number 2. This lecture we're going to do Tuesday. We'll go for an example. Say we want to divide x to the power of 6 and perform x12 plus x3. Whatever. I'm going to write it down on the next board and use some colors in order to emphasize every step in the process.
Metal is making related.
Yes, yes. Last week, I've already lost one fight with metal. So write it down the way we like to write it down. Never. So step by step. First of all, I divide the greatest power of the denominator with the greatest power of the numerator. X to the power of 6, x to the power of 4 gives us x to the power of 2. Now, what do we got in step A? Multiply with the numerator. We get, right down in red, x to the power of x squared, multiply with this, you get x to the power of 6 plus x to the power of 5 minus 2x to the power of 4 plus 6 x to the power of 2. This is step B, which is written in red. I just want to see the most bueno pintos. Let's take purple instead of red. This is the Zoom people. Nobody's in Zoom right now, okay? So all y'all here. But with the recording in purple. So yet again I multiply it and we got x power of 6 plus x to the power of 5 minus 2x to the power of 4 plus 6 squared. This is step B. And step C says, well, write down the difference between them. One gets minus x to the power of 5 plus 2x to the power of 4 minus 6 x to the power of 2. This is one full iteration of ABC. Yes, as we can see, the power of our little precious is still greater than the power here. When we divide x to the power of 5, x to the power of 4, we do not get a fraction. So we have to continue. Yet again, where's the blue one? X to the power of 5, x to the power of 4 gives us x. What do we got? Which is minus x. Looking per iteration. Minus x, we multiply it with our polynomial, and we get minus x to the power of 5, minus x to the power of 4, plus 2x to the power of 3, minus 6x. This is step B. And step C, write down the difference. Window. You get, it's minus, it becomes plus, so we have plus, we have 3 x to the power of 4, minus 2x to the power of 3, minus say 6x to the power of 2, and minus is plus 6x. Yet again, 3x to the power of 4 is divisible by x to the power of 4, but it's probably going to be our last iteration. We get plus 3. Plus 3, we get this iteration multiplied by our polynomial. We get 3x to the power of 4 plus 3x to the power of 3 minus 6x to the power of 2 plus 18. Forgot our colors. Not very important. Let's give it the standard. Again. 4 3 minus x 2 and plus 18. This is level B and step B and step C. Writing down the difference, we get minus 5 x to the power of 3 minus and 6x minus 18. Now x to the power of 3 is not divisible anymore. When it comes to x to the power of 4, divide, you get a fraction. 5 above x. So we're done here. What do we get? x6 above x4 plus x3 minus x4 plus 6 is our expression. What do we get from the division? And the remainder, the residue, it's not divisible anymore. Hopefully, didn't make any mistake. X4 plus x3 minus 2 x squared plus 6. As usual, when it comes to an equation, one can check that it holds. Do Hebrew it's called מכנה משותף, the common denominator. Put here, put this expression up here, multiply of course with the denominator, open the parentheses, the brackets, organize the little, and see. Do you actually get x to the power of 6? Hopefully you do. If we didn't make any mistake, I'll upload. Now let's think about the big goal. Calculating the integral. Right now, the integral of everything outside the fraction is immediate. This is a polynomial. X squared is x to the power of 3 above 3, etc., etc. We move to the next level, next step from our 3 big steps in the big process. Now, we have a fraction in which the power of the degree of the numerator is actually lower from the degree of the denominator. Now the question is how we move forward from here. As I mentioned, we have to write the fraction as a sum of partial fractions. But what is a partial fractions? What do we actually expect to get? Of course, need another explanation. Let's be mentioning. Any questions? Okay, so this is step 1. We do have like 7 minutes left. So let's start to talk about the next step in the big process. Partial fractions. I will handle this. We can have a very long discussion. Mathematically, theoretically, talking about these partial fractions. How do we write a polynomial as a multiplication of different irreducible polynomials of lower degrees? I don't want us to go there. I just want to write down what is necessary for us to understand the process and move on. You get it from me as true without questioning. Of course, you can ask questions, but I don't want to go deeper into the math beyond these partial fractions. Yeah.
Is that the kind of partial fractions we have to solve exam?
No. This one is a bit harder than I expect from you because the process of writing down the partial fractions requires us to write down the denominator as multiplications of polynomials of degree 1 and 2. When it comes to specific polynomials of degree 3 or 4 or even higher, it is not that difficult. Generally speaking, it's a difficult question. I mean, myself, at least when I'm looking at it, writing it down, try something, I can't see the fractions. Can't see the polynomials which make the big one here. So every this is a mathematical proof. Don't get too wise. True. Every real polynomial. There are fields in mathematics when you discuss only polynomials with integer coefficients. Excuse me. On the other hand, you can talk about complex one. In field, we talk about real analysis, real calculus, and the polynomials are real, which means the coefficients are real, etc., etc. Every real polynomial can be written as multiplication of irreducible. I think that's how you write it. Polynomials of degrees 1 and 2. For example, not this one, but one before was x to the power of 3 minus 1. And one can write it as x minus 1 multiplied by x squared plus x plus 1. And when it comes to such an identity, you should know it. So the R, this one. What irreducible means? Mathematically speaking, that you can't write it down as multiplication of polynomials of lower degrees.
Except from one.
Yes, one is the non-considered is a polynomial for this kind of method. Is you can mathematically define exactly what irreducible means, and one is considered an invertible element of the field, and we don't talk about complicated. Not that complicated, but for a different course, which I don't think you're going to learn. Mathematician's problem. Maybe, I don't know what actually happened in last year or the full sample actually, but no. What irreducible actually means is polynomial of degree 1, which you cannot, of course, write down as multiplications of others, and polynomial of order 2 without roots. Two real roots. Irreducible. It is degree 1 or degree 2 without roots. Very nice. What are partial fractions? Partial fractions are fractions, each of which has only one component, irreducible component of the denominator in its denominator itself. Now I want to write it down in the example, and we finish. We continue, of course, to choose that. And now, partial fraction. Contains only one of the irreducible components of the the denominator. For our example, let's say we have a fraction with x to the power of 3 minus 1 as the denominator. It doesn't matter what the numerator is for the concept. For the specific question, of course, it's important. As we already mentioned, the degree of the numerator is lower. One can get one fraction with x means 1 as a denominator, and the second one x squared plus x plus 1. What do we put in the numerators of our fraction? That's what we're going to explain in our next lecture. But the concept of what we expect to get when it comes to denominators is this. Every component, every irreducible component of the denominator should have its own fraction. And we call such fraction a partial fraction. Yet again, the big goal is to calculate the integral. And when it comes to such fractions, the integral is immediate. It's ln. When it comes to these integrals, then we go to step 3 of our process. But first of all, we have to finish step 2. And we already finished our lecture now. So as I mentioned, after a good reminder, we'll talk about it next lecture on Tuesday. Any questions, guys? It's gonna be fun and games. Just without the fun and the games. You always have to remember, if your degree, your BA, whatever it is called, was easy, the salary afterwards would be significantly low.
And obviously people that do a course instead of coming to university usually get it easier.
Let's say with the current state of the market and employment in high-tech jobs, doing one course is probably not going to get you a nice job.
I just got into